Are you all getting sound on this video?
No.
Cool. And cool, so that's good, because there's going to be a lot of videos in the actual lecture today. Oh, thanks. Figured I should wear a shirt that was not volcano colored so I wouldn't like blend into my background. Everyone doing all right? I found this video while I was putting together, just putting some more videos into our lecture. Because I was looking at from the last time I taught this class, there definitely weren't enough videos. And this one was just like a little too long to put in there, but makes me nervous how close the camera is to this. Like another thing that movies likes to do with volcanoes that's wrong is like they'll have like an open hole at the top that like, oh, you can fall in or whatever, and that like occasionally lava will just like come up the tube and out the hole. But as you can see in this, that's not what happens. Like there's actually, I think the time bar is over it. But the like when it's not erupting, it's just like rocks. And that's part of the whole thing is like if it were just open, it would be easy for lava to just get out and you wouldn't really have explosions so much. But in this case, it actually has to sort of percolate up through the existing rock and then blast some stuff out of the way. So it'll show that again in a second, probably. My week's been all right. It's been, I mean, I've been working. Had a headache from the bad air still, but hopefully, well, has your week been good? All right. Actually, I guess it's 2. So I'm going to just turn the sound off on this for now. All right. So I'm going to leave this playing. Oh, you had an exam yesterday. Well, we have an exam next week. Oh, you have another one today. Yikes. Well, I'm sorry that I guess this is probably midterms time for many classes, right? So like I was saying the other day, like we don't have a true midterm in this class. So we just have, oh yeah, see, there's what I was talking about. It was just like a pile of rocks that then it exploded. But yeah, we don't have a midterm in this class. We just have sort of the 4 regular tests, and they're all going to be like the last one. They're going to be 30 multiple choice questions, and they're just tests. They're not midterms. They're not whatever. And like I was saying before, the lowest grade of those 4 will drop at the end of the semester. So if you did really badly on the first one and then you studied harder and do better and better, the first one won't count. Or if you, like, let's say that you are really sick and can't take a test and you miss one, it's not a big deal. It'll go away if you do the other 3. So trying to make them, I mean, I still need to sort of test you on what's going on, but I don't want it to be like super high pressure. So on that topic, yeah, our next test is 1 week from today. So it's going to cover volcanoes. So the stuff that is in today's lecture will be the last stuff that's going to be on the next test. And again, it's on Wednesday, the 14th. We do not have class on Monday, the 12th. And I'll email you again to remind you of that. But that next test is going to work the same way as last time. So we're going to meet in here on Zoom at 2 o'clock and do about 25 minutes of reviewing. So after class today, I'm going to put up another like submission box for if there's stuff you want me to go back over in those 25 minutes before class, or before the test, sorry. And then at 2:25, we'll turn off Zoom, and 2:30 to 3:15, you'll have to do, it's again, another 30 question multiple choice test like the last one. And so, yeah, and that'll be all of the igneous rock stuff, all of the volcano stuff, and then the general rock definition, rock cycle stuff. So any questions about that? All right. So hopefully by now you all have and know how to use Lockdown Browser. But if you didn't get that figured out for the last test, or if you were having any problems with it for the last test, definitely make sure you have it working in advance this time. Because it's one of those things that, like, as you probably noticed, if you were having trouble last time, if it's not working, then it takes up time. So that fake test is still up there that you can use to test that browser on different devices. But I definitely strongly encourage you to test it before next Wednesday. Even if you had it working last time, if you think you're going to be using a different computer or something, or a different, internet connection, even just test it to be sure. Just make sure everything's working. And so that way, if you test it before Wednesday and you find out that it's not working, you can contact me and we can get it fixed before the test. But yeah, and then after that, starting the following week, we're going to get into sedimentary rocks. But yeah, I guess I can pause this video. By the way, this is a volcano in Indonesia called Gunung Ibu, and really kind of impressed at how close the camera is to this. Yeah, so there's going to be one more quick quiz that's going to go up after class today, and then I'm also going to go through last week's quick quizzes and update them to be the correct number of points. In terms of studying for the test, look at those study guide bullet point things again. Look at the answers to all of the quick quizzes, because I put explanations of all of the different choices on them, so you can go back at them and go back to them and look at the answers and look at sort of see what you did. And I have one more office hours session before the test, so that is Tuesday from 2 to 4 on Zoom. So no actually coming into my office. So yeah, any logistical anythings, questions, confusion, concerns? All right. then if there is nothing, I'm going to finish with volcanoes now. And if you do think of something that's about the test or about logistics, either, maybe hold on to that for the end of class. But yeah, let's switch this over to our lecture. All right. So today we're going to basically go through a bunch of different kinds of volcanoes and what they do and how they behave differently. And so there's going to be a lot of pictures and a lot of videos today. But yeah, so we ended with this slide last time. So last time we talked just about what a volcano is and how they work. We talked about how it is a vent that allows magma to come out of the Earth's surface and erupt as lava onto the surface. And usually it forms a mountain, not always. But so the volcano is both the vent that releases the lava and the mountain that is formed by the lava pooling up. And we talked about the 3 V's of volcanism, the 3 V's of explosivity. So volume, which is how much rock is involved. Viscosity, which is how sticky it is, how easily it flows or not. And volatiles, which is gas, how much gas is in there, how much gas is trapped in the mineral structure. And so viscosity is controlled entirely by mineral structure. It's controlled entirely by how those silica tetrahedra stick together. Then volatile content is controlled by the viscosity because the shape of the minerals allows gas to be trapped or not, but also just by how much gas is there. Like no matter how viscous a lava is, if there's no gas, there's not going to be gas in it. So it has to be there in order to be involved. But the more viscous the lava, the more gas, the more volatiles it can trap. And then the volume is just controlled by how much molten rock there is. Like you can't have a big eruption if you only have a little bit of magma under the volcano. So it's really the combination of all 3 of these things that control how big of a boom you're going to get. And in general, it's the more of all 3 of them, the bigger the explosion. So if you have a high volume, high viscosity, high volatile situation, you're going to have a really big eruption, or at least the potential to have a really big eruption. Or if you have low viscosity, low volume, low volatile content, you might have a little bit of oozing, but not that much to worry about. It'll be a very effusive eruption and not a very big one. But in general, like if you have low volume, low volatiles, high viscosity, actually that's not going to be explosive. But usually it's the higher the volatiles and the higher the viscosity, the more explosive it's going to be. And then the more volume, the bigger the eruption. And so, and all of those things, what's the viscosity, how much gas is there, how much stuff is there at all, is controlled by what kind of plate tectonic situation this volcano is in. So you can get volcanoes in subduction zones. So like if you have an oceanic plate subducting under another oceanic plate, you get what's called a volcanic island arc. So just a whole string of islands that have volcanoes on them. And because that's ocean crust and ocean crust, all of that is very mafic. It's a lot of metallic stuff. And so it's going to be either mafic or intermediate in its chemical composition. Because once you start building those volcanoes up and you get more material that's further from the inside of the Earth, it's colder up here than it is down here. So you start to get some fractional crystallization, which is you start to get some things where the stuff that's more mafic cools lower down and the stuff that's more intermediate is hot higher up. So you can get mafic to intermediate content on volcanic island arcs. And because it's a subduction zone, because this is pulling a bunch of water down because it's in the ocean, you have high volatiles. So this is going to be a pretty explosive situation. Meanwhile, in a continent ocean subduction zone, that oceanic plate is mafic, but that continental plate is felsic. And so all of this really hot stuff is going to melt the felsic stuff. Whoops, come back. No, don't play the video from last time. Okay, all of that is going to melt the felsic stuff. And as a result, you have molten felsic stuff, which is very viscous. And again, because this oceanic plate is dragging all of this water in there, you have high volatiles in a high viscosity situation. So the rocks here are going to be intermediate to felsic, they're going to have a lot of volatiles, and so you can get very big explosions in these continental volcanic arcs. So those are your convergent settings where you get volcanoes. The volume is usually going to be moderate. It sort of depends on each individual place. You can have a small volcano, you can have a big volcano in that setting. Then you can also get volcanoes in divergent settings. So if you have a continental rift where the crust is trying to pull apart and a continent is trying to split, it's continental crust, so it's felsic. But it does get more mafic over time. And that's because as this stretches and stretches and stretches, the continental crust becomes thinner. The felsic material becomes thinner, and the more mafic stuff that's in the lower crust and the upper mantle gets closer to the surface. And so as a continental rift goes over time, it eventually turns into a mid-ocean ridge, which actually I should have put these in the other order. But in a mid-ocean ridge, it's just two oceanic plates pulling apart and just letting stuff from the mantle come out. And that stuff is mafic or ultramafic. So in this case, in a mid-ocean ridge, it's low volatiles, because even though it's in the water is surrounding it rather than evaporating. So these are very effusive, not very explosive. In a continental rift, they can be pretty explosive at first because it's a rift, but it's in a continent. But it gets generally less explosive over time as the magma becomes less, as the lava becomes less viscous. And then the last situation is where you have a hotspot under a plate. And so that's not at a plate boundary at all. That's just wherever that hotspot happens to be, wherever that superheated plume of material shooting up from the outer core through the mantle through to the crust happens to hit. And so if it's under an ocean, you get a very mafic, high volume volcano. And if it's under a continent, you get a very felsic, high volume volcano. So the location of this makes all the difference. So as we go through different kinds of volcanoes today, I'm going to tell you sort of how viscous it is, how many volatiles there are. Volume really depends, but in general, there's some rules. And we're going to talk about how they explode and just then which of these settings they're associated with. So before I go on and do that, so I'll be using these pictures kind of as an index. But are there any questions about what's happening on this slide before we go through our introduction to different volcano types? All right, don't see any hands. And again, you don't have to raise the hand if I ask. You can just speak up or type it in the box. But yeah, let's talk about different kinds of volcanoes. And in general, I'm going to go from least to most explosive today. So we're going to end with a bang. But yeah, so we're going to start with our mid-ocean ridges and fissures, our mid-ocean ridges and continental rifts. And so hopefully you're very familiar with mid-ocean ridges now. We've talked about them in a lot of contexts in terms of just being a plate boundary, in terms of them being volcanoes, in terms of them being how the ocean floor grows and how things split and move. But in this case, they're volcanoes. They're really, really long volcanoes. And actually, before I continue, I should mention that so this is a kind that doesn't make a mountain, but of the kinds of volcanoes that do make mountains, there's over 1,000 active ones on Earth. Active means they're either erupting or have the potential to erupt at any time. And among those, on any given day on Earth, about 20 volcanoes erupt. And usually it's a small eruption. Like most of the time, they're not an eruption that's big enough to make the news, or in a place where there aren't a lot of people and it doesn't matter. But volcanic eruptions are actually quite common, and there's probably a volcano erupting somewhere right now. But some of those eruptions are at mid-ocean ridges. And so this is what one looks like when it's not erupting. It just looks like a crack, it just looks like a fissure in the ground, because that's basically what it is. Because even though it is kind of like a gateway down into the mantle, basically, because the ocean is cold, when it's not actively erupting, this stuff cools. And so it's not just constantly oozing. There's still an ocean floor that when this does erupt, it'll become molten and spew out. But most of the time, even though you can see, it looks like a long skinny fissure, it's not something you could like fall into and sink into the mantle, no matter what Hollywood says. Yeah, so that's what a mid-ocean ridge looks like. So the anatomy of these, this is something we've also hopefully familiar by now. Wait, I think I lost a slide. Yeah, I lost a slide. I had a picture of the one in Iceland on land. I showed you that picture before when we were talking about divergent boundaries. So I guess I can put it back in before I upload this. Okay, but anyway, the anatomy of these things, hopefully this will look familiar because it is kind of also what our divergent plate boundaries look like. So we talked about this exact thing in the context of plate boundaries, just now we're talking about them in the context of volcanoes. And so with a mid-ocean ridge, hopefully familiar, you've got two plates, they are moving away from each other. Molten rock is rising up because of decompression and just leaking out the gap between the plates. Hopefully, is that familiar? That's still good? Then on land, similar kind of idea, except the plate is in the process of breaking rather than already being a boundary. So in this case, you'll see often a lot of little cracks. You'll see like, different failures and fissures from the earth stretching from the continental crust becoming thinner. But usually the volcanic fissure itself is in the middle. It's at the thinnest part because that's where it's the easiest place for stuff to get out. Like if it's really thick rock, it's going to be harder for lava to melt through and poke out. So at the thinnest point of stretching, like if you think about it, if you're tearing something, like you're stretching a piece of rubber, like a rubber band, when it snaps, it's going to snap at the thinnest part in the middle, right? Well, it's kind of the same idea here, except it's not necessarily snapping. It's just the easiest place for lava to get through. And so when one of these things erupts, it makes a curtain of lava. We actually call that a fissure eruption or a lava curtain. And they're pretty spectacular looking. So before I show you some videos, any questions about just the anatomy of these volcanoes? Just long, skinny cracks that lava come out
of. Can you go over the ocean anatomy one more time?
Yeah, so it's a boundary between two plates. It's basically one oceanic tectonic plate is moving one way and the other is moving the other way. They're moving away from each other. And because they're moving away from each other, there's this gap, there's this separation. And so there's just a space that lava can come out of. It just leaks out very, very easily. So these are not explosive at all because it doesn't need to blast anything out of the way. It just leaks out in a long line that marks the edges of the two plates. Does that answer your question?
Yeah, thank you.
And I'll be putting these slides up today after class. It'll probably take a little while because there's videos in them and it'll be slow, but it'll go up today. So everyone else good with this slide? Cool. All right. Then, so I'm going to show you some video of what these do. So underwater, where do I want to start this? There we go.
I was the chief scientist on this expedition, so I led the cruise and the trip to the West Mata eruption. The video that you'll be looking at is large magma bubbles. They're about 3 feet across, and the bubbles are molten rock that are expanded under the pressure, the gas pressure of magmatic gas. And the magmatic gas, we presume, is mostly water. And when the water is under the magma, that magmatic temperature is thousands of degrees. And when it's suddenly cooled by coming in contact with the water, the bubble bursts. What excites me the most about this volcanic eruption is that on planet Earth, this is a process happening all the time, yet we have never seen it happening in quite this way. The ocean floors are formed almost exclusively by volcanic activity.
Yeah, So you were able to hear his voice, right? Okay. So yeah, this is, even though mid-ocean ridges are they're really common, they're extremely long, there are thousands of miles of them on Earth. Because they're not all erupting all the time, actually catching which spot on those thousands of miles of system is actively erupting at any given time is tough. And also then making sure you get something down there to watch it is tough. So this is really rare footage, but that's what a mid-ocean ridge volcano looks like. It's just some oozing and bubbling, some gas coming out, but also just a lot of steam from this cooling instantly the second it hits the water. So that's not explosive. I mean, that's something that like it's happening at the bottom of the ocean and you'd never know on the top of the ocean. It's just oozing. It's kind of the epitome of effusive. Meanwhile, on land, it's a little more dramatic. So this is Eyjafjallajökull in Iceland. You can see this is just, it's a curtain of lava, that's what it is. So what happened here is because Iceland is both a mid-ocean ridge and a hotspot, there's a huge that's why enough stuff erupted that it turned into land and not just under the ocean. And so, do I have any more? Yeah, there's more fissure. Yeah, and so occasionally it'll behave like a mid-ocean ridge and just keep stretching, and you'll get exactly the same idea, a long skinny crack that happens to be letting curtains of molten rock out. And so it's, you know, you wouldn't want to like be in that. But at the same time, it is, I mean, they're able to get pretty close to it with cameras and stuff because this is still fairly low volatile stuff. So it's low viscosity, it's basalt, it's very runny. And so it's able to fountain very dramatically, but because there's actually not a whole lot of volatiles in there, it doesn't spray very far. So it's pretty contained, which is why it tends to take up that kind of curtain shape. So any questions about that? About either of these kinds of rift eruptions? Again, it's basalt, it's low viscosity, low volatiles because it's spreading things, but not necessarily like dredging up more volatiles. And the volume can be low, it can be high. In this case, in Iceland, it's pretty high. In the ocean, it varies. Any questions about rifts or ridges? All right. Yes. And let's move on to something a little bit more typically volcano looking. So like the stuff that causes rift eruptions, like you wouldn't necessarily look at that and go, ah, yeah, that looks like a volcano, because it's not a pointy mountain. But everything else we're going to look at today is kind of a pointy mountain. Although shield volcanoes are so named because they're not so much a pointy mountain as a very gently curved mountain. And the reason for that is this is a place where you have low viscosity, low volatiles, and extremely high volume. So you get shield volcanoes where you have a hot spot under an oceanic plate. So this is that case where there's the super, super, super heated plume coming up through the mantle and burning a hole through the crust, like in Hawaii. And because it's so hot, it melts freaking everything. So the volume is very high. But because it's just coming straight up, there's no subduction to draw water down into it. There's very low volatiles. And again, the viscosity is low because it's mafic. It's all basalt. And so the eruptions you get from these are effusive. You have runny lava flows and you have fountains that, again, there's some volatiles in here, but they're generally very confined. Like this fountain is gonna kind of stay in its radius. It's not gonna explode everywhere. So you get fountains where there's a little more gas, flows either where things are just oozing out, or in this case, like the fountain, everything is splashing back down and then pouring out into these lava flows. because basalt is so runny, because it is so non-viscous, it doesn't pile up in a big pointy mound. It flows into a much more gentle slope. So before I move on to that, any questions about the basics on shield volcanoes? Low viscosity, low volatile, high volume lava flows and fountains. And this picture is of Hawaii down here. So again, it's called a shield volcano because the shape is kind of like, if you think of like an ancient Greek or Roman shield, like one of those, a round curved shield, and you lay it down on the ground, it's going to have a gentle arc to it, but it's not going to be like a cone. And so shield volcanoes form that way because basalt just runs so easily, it just flows so easily that it pours down to the sides more than it piles up at the top. So looking at one of these on the surface, it's not even going to necessarily obviously have a slope. Like you might have to stand pretty far back from a shield volcano to realize you're on a slope at all. But when you consider that these things are coming up from the bottom of the ocean floor, they're actually some of the biggest mountains on Earth. So sometimes we talk about, so Mount Everest is the highest point above sea level. It is the biggest mountain from zero elevation to the top. But if you go from the bottom of the ocean to the top of a mountain, actually Mauna Loa in Hawaii is larger. Mauna Loa by volume is actually the most voluminous single mountain on Earth because it is just a massive, massive, massive amount of lava coming up that starts piling up all the way on the ocean floor and goes all the way up to over 10,000 feet above sea level. So it's huge, but it looks just kind of like a peaceful, gentle island because just it's so, the part of it that sticks out above the water has such a slight slope. And I'll show you some pictures to kind of emphasize that. But does that idea of why very runny liquid would make a very gentle slope make sense? Like imagine trying to make a pile of water as opposed to a pile of honey or a pile of sugar cubes. This is, I mean, it's more viscous than water, but in terms of lava, it's more like water than like sugar cubes. But yeah, a shield volcano is made entirely out of just layers of solidified basalt. It is 100% basalt, pretty much, just layer after layer after layer. And the layer structure is just from flows, coming up overflows, over and over and over, just building up over time. But those layers can actually be made of a couple of different kinds of lava flow. And I'll get back to that in just a second. But first, so again, I showed you this picture last time. This is the top of Kilauea volcano in Hawaii. This picture is from 2009. So actually this hole has gotten larger in more recent eruptions. But does this look like a slope to you? Like, do you see much of a like curve in this picture?
No.
Yeah, it's a really gentle slope. This is actually the top of Kilauea. It's just, it's such a broad thing that you can't see it up close. But let's zoom in on the wall of that crater. Can you see all of these layers? You should hopefully see stripes here. So these are all different lava flows. These are just different eruptions over hundreds of and thousands of years building up the crater wall and the whole mountain. Like it's exposed here because this part either blasted out or collapsed in. Because sometimes there's enough volatiles that you can get explosions, but that's pretty unusual. But yeah, if you were to like dig a pit down to anywhere else in this volcano, although perhaps ill-advised because you might let the lava out, you would see layers like this. So that makes sense. This building is the Hawaii Volcano Observatory, by the way, but I think if I remember correctly, they have had to move it since eruptions in 2018 kind of damaged this pretty badly. But yeah, As I said, there are a couple of kinds of lava that come out, a couple of different textures of lava that come out of these Hawaii-style volcanoes. And there are shield volcanoes in other places in the world, but the ones in Hawaii are the most famous. Like sometimes you will actually see people call a shield volcano a Hawaiian-style volcano, or say something has a Hawaiian-style eruption. But yeah, one of the kinds is a really kind of chunky lava that's called a'a. It's a Hawaiian word. I don't know if it literally means the sound you make when you step on it, but that's the joke, is you go a'a when you step on it. But this kind of flow, it's chunky, it's thicker, it moves kind of by tumbling. I'll show you what it looks like.
The heat, I would say it's what I'm feeling. I'm standing 20 feet away, about 130, 140 degrees Fahrenheit. And it's advancing to us. I think it's faster than a turtle can move, but less than a mile per hour. And again, I'm still on Makame.
Yeah, so I guess I can turn the sound off on that and keep it playing. So as you can see this moving, as he pans away, it moves by sort of rolling. This guy's, so you can see, he's saying it's moving less than a mile an hour. So this guy's probably very uncomfortable, but like, this isn't moving very fast and it's not blasting. It's just kind of rolling over. And that's how these things flow. And when a'a hardens, it's very sharp and chunky and will tear up your shoes like nobody's business. But this is still basalt. This is still not very viscous at all. And so you might notice, well, that's still pretty viscous. It's still oozing very slowly. But yeah, for lava, that's not viscous. And then the other kind of flow that you can get on a Hawaiian volcano is something called pahoihoi. And so here's, I'll play the video first and just notice how this stuff moves.
8:24 a.m., May 27th, 2018. I'm Scott. This is the official channel for Apau Hawaii Tours. No spaces on YouTube. My goodness, you guys, I'm speechless. You are I think this is the first time I've seen this. Look at how fast this is moving. We're on Luana, looking towards Leilani. Right over there was the first burning house I got. Oh my goodness. We got, this power pole is gonna go down pretty soon, and I'm not trying to be extra dramatic or anything, but here we can actually see, this is the first time I think, seeing how fast, there goes a text.
Is it healthy to be that close? Actually, it's not as bad as you would think.
It's probably 130, would you say? 130 Fahrenheit. Speechless. Absolutely speechless.
I'll answer more in a second.
A perfect example of pahoihoi lava.
Yeah.
My goodness, you guys. Okay.
So this guy's YouTube channel is great because he's just really excited about lava like all the time. But yeah, so the reason it's actually not terribly unhealthy to be that close is this is actually, again, very, very low volatile content. So, I mean, the heat is no joke. It is really, really, really hot. I have stood this close to this kind of lava. It is so hot. But there's very little gas involved, so it's not gonna like mess up your lungs, and there's no ash coming out of this. So there's kind of nothing that's really going to seriously hurt you other than if you tried to touch this, and don't be that stupid. Just don't touch the lava, don't touch the lava. But yeah, this is very uncomfortable. But you also might have noticed him saying this is fast for pahoihoi, and it's not that fast. You could easily get out of the way of this. Yeah, I kind of want to touch it though. Like it's pretty, it's shiny. It's not soft. It's actually I have jammed a stick into something like this, the forbidden slime. You would burn yourself instantly. You would probably burn the flesh off your hand instantly if you touched it. But you can jam a stick into it, and then you realize it's actually not very soft at all because it's still rock, very dense rock, in fact. But yeah, notice how the last thing you'll ever touch, please don't, please don't do it. But yeah, you notice how while the was kind of tumbling over, This is just kind of oozing and flowing and making a kind of ropey texture. So it's actually, I think it's a matter of just a little bit of volatile content, a little bit of dry, cooling temperature. I don't think it's still very well understood why and Pahoehoe are different, like why this happens, but it does. And by the way, I paused the video just because he talks about some other stuff, but when I upload this on Canvas, the whole video will be there. And actually, again, this guy's YouTube channel is pretty great because he's just excited about lava and also has 2 dogs. But anyway, yeah, so and Pahoehoe are kind of what you're going to get coming out of these shield volcanoes. And it's not fast. Like there are places where like when you're really close to where the lava is pouring out of the top, you're going to get these channelized rivers of lava that do move very fast, but like they're channelized rivers. They're very contained. And so if you don't like step in them, you are not going to get caught by it. So as much as like, yeah, you need to be cautious when you're walking near this stuff. The reason it is kind of relatively safe to take a tour to a Hawaiian volcano is because really they just ooze. They just do this like a lot. But sometimes, like you can see here, this person's house is having a problem. So the 2018 eruptions of Kilauea, right before it actually stopped erupting, really did destroy a lot of homes because like you can't stop this stuff. You can just leave, but if your house is in the way, your house is in the way. Whoops. Any questions about and Pahoehoe? They're Hawaiian words. I'm not gonna, again, you're not gonna have to spell those. I mean, although is literally just but recognize them, know what they mean. Any questions about those? Cool. Oh yeah, and sometimes lava pulls up without flowing. Sometimes you can get what's called a lava lake, and it's just going to hang out and kind of bubble. So this is not a photoshopped picture. This is an actual photo of Kilauea in Hawaii, which I think went viral and made memes. I think there was a meme that was like, local volcano is having a great day. But yeah, lava lakes are just like, you can have just a bunch of lava that's hot enough to not cool over. Like it's hot enough to maintain its molten temperature even in the air, which is pretty darn hot when you consider that it's basalt. It has the highest melting temperature, but also the highest cooling temperature. But it's just, there's not enough either volume or volatile to actually push it out of that crater. So it just hangs out until something changes, until something pushes it out, or until it actually cools over, or until it sinks back in. Any questions about that or about shield volcanoes? Cool. Then let's get into some stuff that, oh wait, no, I've got one more that doesn't blow up before we get into ones that do blow up. So our last effusive kind of volcano, our last kind that doesn't erupt in an explosive way, is called a lava dome. And I actually talked a little bit about these last time when I was talking about how rhyolite flows, because rhyolite is so viscous that it doesn't really flow. It just kind of glorps, just kind of piles up. So lava domes, but sometimes they're in an existing volcano and sometimes they are their own volcano. It just kind of depends on where they are. But by definition, they're high viscosity and low volatiles. And the reason that's true is like if they were high viscosity and high volatiles, they'd explode. So in this case, there's just not enough gas in there to make this stuff do anything other than just glorp. So you just get a slow buildup of lava just kind of rising out of the ground. And these are often associated with more explosive volcanoes. They're often affiliated with volcanoes in subduction zones. They're often related to hotspots. Sometimes they're on their own though. So they can actually exist in most of the tectonic settings that I mentioned before, except for in rifts. Well, I guess you get them in continental rifts, but not in mid-ocean ridges. It just kind of depends on just what you got there. Is there some magma left that can't be exploded out of the volcano? Or is there just not the right kind of thing to explode? So lava domes usually form in a single eruption and don't erupt again. Sometimes they will then continue to grow. It really, again, depends on where they are. Like, so this one, this is in the crater of Mount St. Helens, which is known to be an extremely explosive volcano that we will talk more about later. But after it finished exploding, or actually in 2004, it exploded a little bit, but then just kind of shot this thing up. And then it got a little bigger in 2008, and we'll see. But in general, this is something that, like, it's a very, like, there will be some signals. You'll see earthquakes related to the magma moving inside the volcano. But in general, this is a very gentle situation. It's not a particularly dangerous eruption because it's so slow, and actually usually because it's magma that's lower temperature as well. But I forgot to turn off my email, sorry. So any question about, just in general, why you need high viscosity and low volatiles? And usually low volume, sometimes more, but the high viscosity and low volatiles are key for this to pile up like this. So that makes sense? So I don't really have a video of one of these erupting because they're so slow and not particularly exciting, but I promise you more videos later. But yeah, so this case, you can get them in the crater of a more explosive volcano. So like this example at Bezymeny volcano in Russia, it's a case where this was another really big explosion. And then after all of the volatiles got gone, this lava dome piled up inside the crater and is actually starting to look almost like a secondary volcano, like a secondary cone and not just a blob. And so this is just after this blew up, this is the remaining lava just glorped up into this secondary cone, which now looks like it's starting to have its own crater. So you might get craters within craters within craters. But this is a lava dome directly inside another volcano. And also, fun side note, Bezymeny means no name. So I think this is a case where probably someone went to Siberia and were like, hey, what's that mountain? And they probably said, it doesn't have a name. And the other person went, okay, cool, Bezymeny. A lot of volcanoes just have names that mean like fire or explosion. Kilauea means spewing. But yeah, this one means no name, just as a side note. So that's a lava dome inside another volcano. This example then, Black Butte in Northern California. So if any of you have ever taken the 5 all the way up into Northern California, this thing is right next to Mount Shasta, which is, I mean, this is big, but Shasta is like way, 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 way bigger. But this thing is a lava dome, and it is associated with the same magma chamber that fuels Shasta. But in the case of Shasta, and Shasta is a subduction zone volcano, which we're going to talk about soon. But there's a lot of volatiles under Shasta and feeding the vents that are directly related to Shasta. But this is kind of a subsidiary section of that magma chamber where just there aren't as many gases. And so in this case, this thing has kind of glorped up over time next to the more explosive volcano, but without necessarily exploding itself. And so in this case, it's super pointy because it's made out of rhyolite. It's very viscous. And so it's able to maintain this extremely pointy shape as it kind of pokes up out of the ground. But you're never going to get an explosion directly coming out of the top of this like you would with something like Shasta. But these things can still get really big. Yeah, and so this is still associated with subduction. Although in this case, just the volatiles are not in the lava dome, even though they are in the main volcano. So does that make sense? You can also actually get lava domes in spreading places. So, so this is in Baja California. Cerro Prieto is actually pretty close to SoCal. It's not that far south of the border. And this thing, so it just looks like a blob of black rock, which is probably why they named it Black Hill. But it just looks like a blob. But this thing is actually a lava dome as well. But there's no subduction though. So what basically is the Gulf of California, Baja California used to be attached to the rest of Mexico. But then the transform boundary, the San Andreas Fault sort of kind of started moving things north. And just because of the angle of that movement, it tore Baja away from the rest of Mexico and is kind of opening up the Gulf of California. And so there's a divergent boundary forming in there. And in that case, in that kind of setting, there's not a lot of volatiles, but because of the stretching and tearing, the crust there is very thin, and there's a lot of heat very, very close to the surface of the Earth. So that's also why like there's a lot of geothermal energy around the Mexico-California border because of this. But in this case, there was enough heat coming from that rifting to melt some stuff. And so this thing is made of andesite, so it's intermediate composition, because it still has to melt through the crust. It has to melt through the continental crust. But because the continental crust is so thin, a lot of that more mafic basaltic stuff is mixing with it. But because it's rifting, there's no volatiles involved. So all this thing can do is just kind of glorp up. Does that make sense? Basically, you get lava domes kind of anywhere where you have stuff that's hot and it's close to the surface, but there isn't really a lot of gas to propel it up. So it just rises by decompression and by flux heating, not by flux heating, just by contact rather than by getting blasted out. So that's about it for lava domes. They're not that, I mean, they're interesting. They tell a lot about the eruptive history. Very often you'll get lava domes after larger eruptions, or you'll get them when like a plate boundary is starting to change. So they're very interesting from a standpoint of putting together the history of what happened, of putting together the plate tectonic history and the volcanic history of a place. But in terms of like eruptions and cool pictures of lava, they're not exciting. I'm sure there's people who spend their life's work on lava domes whose ears are burning right now are gonna come and kick my ass for saying that. But when you think about volcanoes exploding, these don't. And any questions about lava domes? All right. Now we're gonna get into stuff that blows up. Okay, so we're gonna be kind of moving up the explosivity scale now. So all of these three, rifts and fissures, shield volcanoes, lava domes are effusive volcanoes. They leak rather than blowing up. But now we're going to get into explosive volcanoes of different scales. Oh wait, sorry, I forgot one more lava dome thing. It's a blob. It's just a blob of lava. The pyroclastic stuff there is usually left over from something else. A lava dome cannot itself cause a pyroclastic flow because you need to have explosions to do that, and these don't. That's just saying it's poked up through the remnants of some other volcano. But yeah, it's a blob. Moving on to explosives though. So cinder cones are a kind of explosive volcano, but they're generally pretty small. So these are medium to low viscosity. They're going to be basalt or andesite. So because of that chemical structure, they can't hold a whole lot of volatile in the chemical structure, in the lava. But the situation that they're in still generally has high enough volatiles in it to blow that stuff up anyway. And they usually are pretty low volume. So cinder cones are usually pretty small. And they actually usually only erupt once and then stop forever. They usually represent like, here's a small pocket of magma that has enough volatiles in it that it just needs to get out, and that gets out and then it's done. So most of the time when you find a cinder cone, it's going to represent one eruption and that's it. But yeah, they have medium to low viscosity, so they're able to still ooze and fountain. High volatiles, which allows that explosiveness to happen even though it's low viscosity. And low volume keeps the things pretty small. They happen in a lot of tectonic settings. So this might also be another thing where you'll get these in association with a bigger, more explosive volcano. Or you'll get them, like you can get these associated with subduction zone volcanoes, like, or you can get them associated with spreading centers. It just kind of depends on the local conditions, because they're so small. These volcanoes are so small that often just even a local sort of anomaly, even just a spot that is locally hotter than it should be or has more gas than you would think it would in that spot, can make one of these, and then it erupts and it's done. Yeah, so they're kind of a little bit of a wild card. They're also really common. And actually there are old cinder cones in California. But again, they erupt once and they're done. So yeah, these exist in a lot of different places, and they're explosive, but they're small blasts. You get small blasts, you get fountains. Fountains are very, very typical for this. And in this case, you can see rather than like flows pouring down the side of this, there's a lot of just streaks of just individual chunks and lava bombs rolling down the side of this thing as it erupts and grows. And actually the reason it's called a cinder cone, in fact, is often we call these little tiny lava bombs, these little chunks that get blasted out in the eruptions of these, we call them cinders. You might also hear the word tephra. Let me write that in the chat, tephra, or scoria. So tephra cone, scoria cone, cinder cone, those are all the same thing. I'm going to use the word cinder cone. I think that's the word your book uses all the time. But all three of those things, cinder cone, tephra cone, scoria cone, are the same thing. And they're caused by these little bits of low viscosity stuff getting launched out of the volcano in a high volatile situation. And then these individual chunks cool in the air, because they're usually pretty small, and then pile up as they fall back down. Does that make sense? Yeah, just throwing things in the air and then they just pile up. These are usually pretty short, and they're usually very, very conical, because they're usually just a fountain in the middle and everything coming down pretty symmetrically down the sides. So they're really going to be often extremely, extremely symmetrical. So here's an example. So here's an example of some cinder cone activity on the side of Mount Etna in Italy. So Etna is actually a subduction zone volcano, but it has this spot on it where it's more mafic. And so it has this cinder cone. And these are real sounds, by the way. This is what this actually sounds like. Just listen to it for a second. So you can see, rather than this necessarily being a lava flow, let me turn it down a little. This is a lava flow. But you could see before, sometimes if enough stuff comes out, you will get flows. But see how there are these little like pieces that are just tumbling down the side rather than flowing as a river? So that's tephra, or scoria, or cinders. Those are the things that pile up. See, it's getting shot out in chunks. And that piles up to form the sides of these mountains. And so if you were to hike up a cinder cone, and there are places you can do that in California, it's just going to be lots of little chunks of rock rather than being a solid sided mountain. But yeah, this is what they do. They just, a lot of gas with some rock in it just blasts these spatter. Actually, spatter cone is another word for this, in fact. Yeah. So I would definitely, so Alexander said this is scary. I would definitely be more scared to stand really close to a cinder cone than to Hawaiian volcanoes. And that's because there's a lot more gas involved in a cinder cone. And that spatter is going to go a lot further. But on the grand scheme of things, though, these are pretty small. And so yeah, I'm gonna pause this here. This video is actually like 5.5 minutes long. But if you want to watch the whole thing, it will be up as part of this PowerPoint on Canvas later. But yeah, so the anatomy of a cinder cone then. So I mean, this kind of looks like your classical volcano, right? You've got your magma chamber and your conduit and a nice pointy mountain with a fountain of lava coming out the top. Like this is your absolutely classical cartoon of a volcano. And so, and that's basically what's going on. And so you get layers, there's some lava flows if you get a lot of stuff coming out at once, kind of depends on the volume of the individual cinder cone. You get a whole lot of, so actually lapilli is another name for tephra or scoria, don't worry about it. But you get, so these are layers of lava and ash and little chunks of stuff, of cinders, of scoria, of tephra, of lapilli. And in some cases, so this is explosive enough that it can release some ash, but it's also a small enough explosion that this isn't going to like choke everyone out with an ash cloud. And you can, in a rare occasion, get a pyroclastic flow from one of these, because a pyroclastic flow just requires a lot of gas and a lot of ash. And so if you have a situation where it's a particularly intense cinder cone eruption, you can get a small pyroclastic flow out of one of those. But again, it's not very common and they're not very big. So really, even though that looked scary, and even though this is, little chunks of molten rock getting launched everywhere, and actually I think this picture in my background is a cinder cone. Even though you see stuff getting launched everywhere, it's generally not gonna go very far. You can generally get away from this volcano and not be affected by it because they affect a pretty small area. But yeah, it's a cone. It's layers of lava and ash and chunks of tephra, scoria, cinder. And so again, they make really perfect cones. Like, look how beautifully symmetrical this thing is. So this is Paricutin in Michoacan, Mexico. And it looks that it's perfectly symmetrical. This is a round bottom with like exactly evenly sloped sides and a perfect circle up here. I mean, it's really a cone. So I use this as an example though, not just because it is perfect looking, is a beautiful example, but also because this volcano is, it's almost 80 years old, 80. So if you remember, we talked about geologic time and how a lot of things are like thousands or millions of years. Paricutin is 80, actually it's 77 this year. So this volcano formed out of nowhere in 1943. So basically, you might have heard this story or not. It's a pretty legendary story because this is one of that kind of the only case in modern human history of writing down the exact formation moment a volcano formed. And so basically there was this dude and he was just in his cornfield and suddenly he's like, wow, there's a crack in my cornfield and it's hot and nasty gas is coming out and that's kind of bad. Oh no, there's some earthquakes. Oh, that's bad. Oh my God, there's lava coming out. That's bad. And so everyone in the town of Paricutin, so there used to be a town under this, was just like, oh my God, and GTFO'd. And over the course of just a couple days, it grew from a crack in this field to a like 1,000 foot tall pile of volcano. And so here's a picture from, and so this thing actually erupted for 4 years straight, which is unusual for a cinder cone. They usually erupt only for like a couple weeks. But over the course of 4 years, this thing grew to several thousand feet and wiped out the town, like except for this church. And just from this being in some dude's field. And so he, told stories about it. And it's like, it's very much a legend. But this thing erupted for 4 years and then it stopped. Stopped in 1947 and it has not erupted since. There is no sign of heat, no sign of movement. It's just done. But in this case, Mexico is mostly a subduction zone setting. But in this particular case, it's not really a true subduction zone volcano. It's just a little local spot where it was just enough stuff and enough pressure to ruin this guy's farm and kind of the entire town. Yeah, it's a crazy story, but there's if people are interested, I have more videos and footage about this. I found a lot of stuff, but there's only so much time in this lecture. I'm actually going slower than I thought, so I should maybe speed up a little. But I can talk more about that at the end if you're interested. So yeah, cinder cones sometimes do that. There are some of them in Eastern California. So this one is creatively named Red Hill. And you can see it looks kind of chunky. You see like a lot of these chunks of lava. And this thing erupted probably, I think it's thought to be about 10,000 years ago, and then it just stopped. But there's a bunch of these in Eastern California where the crust is slowly getting thinner. And you can sometimes, if you look inside them, so this is another one in Eastern California, you can see that over time, you see how this has like concentric rings? This kind of represents the flow of lava getting smaller over time. So when this thing formed, there was enough volume to make a thing with a hole with a crater the width of this outer circle. But as it started to run out of fuel, then the lava fountain only went this far. And then it ran out of more fuel and it only went this far. And then it stopped. So you can often see the eruptive history of these by just looking at the structures in them. But yeah, these kind of, they do the thing once and then they're done. Yeah. Any questions about cinder cones? Again, this is all basalt. So sometimes they're black because there's a lot of iron. Sometimes they're red because there's a lot of iron and it's rusted or oxidized. But yeah, anything else about cinder cones? All right, then let's keep going. We got 15 minutes and 2 more kinds of volcanoes. We can do this. All right, so I've talked a lot about subduction zone volcanoes without using a name other than that, but that's what we're going to talk about now. The more technical name for a subduction zone volcano is a composite volcano or a stratovolcano. I'm mostly going to say stratovolcano. I think your book says both. These are both common names for these. So this is Mount Fuji in Japan. It's a very classic stratovolcano. And again, this is your archetypal, like beautiful volcanic cone, you know, a little bit of a flat top where you would expect the crater to be, some snow on this one because Japan gets pretty cold. But yeah, this is actually an extremely common kind of volcano. And these are unfortunately also the ones that pose the most day-to-day hazard to people because there's a lot of them. They're extremely common. And when they erupt, it's very explosive. So these are medium to high viscosity. If it's an ocean versus ocean subduction zone, they're going to be andesite, which is still intermediate composition, but pretty viscous. And if it's ocean to continental, it's going to be more rhyolite. So it's going to be very viscous and very explosive. These are high volume high volatiles, because again, that subducting plate is going to drag water down into a place that's really hot, turns it into gas, which helps everything melt and rise. And then they're usually pretty high volume just because this process is ongoing. So there's a sort of sense of just constant refueling going on under these things. And so because you have a combination of a lot of gas and a lot of sticky lava, you get explosions. You don't get so much, you get some lava flows, but they're like those big goopy ones we showed you last time where they're don't flow very far or very fast. But these blow up. You get ash, you get gas, and most importantly, most dangerously, you get pyroclastic flows. Those are the biggest threat from stratovolcanoes. And in that case, sometimes they can be very, very large because these are big suckers. Fuji is a big volcano. Mount Rainier next to Seattle is a huge volcano. These can get very, very large. And so we're going to get a little bit into why they work. But do you get why high viscosity, high volatile, big boom? Cool. So here's an example, another one from Japan. This is Sakurajima erupting just this past fall. And so this is, Sakurajima is very active. It erupts pretty regularly. This is a real-time image, except it's kind of glitching right now. But in this case, you're gonna see, you see there's this cloud coming out, and there's also some lava exploding out of this thing. But you can see there's also a lot of gas and a lot of ash, and you're gonna see this rise up a lot higher than you did for the cinder cone, even though you also have this spatter of stuff going down the side of the mountain. It's also kind of funny. This is such a lovely name. It's Cherry Blossom Island. It will explode and potentially kill you. But it is, you can see this column of gas and ash is going up much, much higher than in the example from the cinder cone. Because in this case, the magma or the lava is a lot more viscous and it is a subduction zone situation. So there's a ton of gas. So stuff just gets launched up really, really far to the point where actually this is called the eruptive column, because it's a column of gas shooting up into the atmosphere. Yeah, they're terrifying. And these are bad news. These, like most of the time when you hear about a catastrophic volcanic eruption, it's a stratovolcano. Like any of those famous ones, Mount St. Helens, Pinatubo, like name a real, Krakatoa, they're stratovolcanoes. Mount Taal that erupted in the Philippines earlier this year, stratovolcano. They're very common and they're dangerous. Because these things, they explode. That is what they do by definition. But why is it called a stratovolcano? So strato means layer. Just like a stratus cloud is a layered of cloud, or we talk about strata when we talk about understanding layers of sedimentary rocks. Strato means layers. And so in this case, you're gonna have Again, it's another beautiful, perfect cone fueled by a magma chamber. There's a conduit. But in this case, you're going to have a lot of different kinds of layers. It's not just going to be lava or just lava and ash. You're going to get a bunch of different kinds of stuff. So this still looks like your basic volcano, right? It's pointy, it's got layers. But those layers are going to be one of four things. They're either going to be ash, which like we talked about is tiny fragments of rock and minerals and glass. They're going to be pumice, which are bigger chunks of glass, but they have a bunch of air in them. So in that case, it's glass because it cools so instantaneously that it can't contain, that it just doesn't have crystals. But in this case, there's also enough gas in them that it doesn't turn into like a solid chunk like you would normally think about glass. It turns into a rock that's actually so light that it floats. Pumice floats, like literally floats, not just floats on rock, it floats in water. Then you can get tephra, which is the stuff we were talking about, like comes out of a cinder cone. It's those small chunks of lava rock that harden in the air and then just rain down. And then lastly, you do get lava flows, but usually those happen last. Usually the lava flows happen after all of the volatiles are out of the way, after the explosion is done, and the rest of the lava just kind of gloops out. So if you were to look at a side section of a shield volcano, it's just lava. Side section of a cinder cone is just going to be tephra and ash, maybe some flows. Stratovolcano is going to be all of these things and pyroclastic material too. So does that make sense why it's called a stratovolcano? So the most famous example, well, not the most famous, but there are a lot of very famous examples. But Mount St. Helens in 1980 is a really good example of what these things can do. So it's in southern Washington, and this is what it looked like before 1980. It's a very classical stratovolcano. It's cone, it's pointy, really beautiful. This used to be a very popular recreational area. But starting in the early 80s, people started to notice the shape of the volcano changing. So in 1964, it was pretty pointy, but in March of 1980, it started to bulge out on the side. And it kept getting more and more. Like you can all see how this side of the volcano is swelling up, right? And while that was happening, gas was building up. People were measuring gas and noticing the movement of magma. There were a lot of earthquakes happening. And they were like, oh, this is the signal that magma is rising up under this part of the volcano and it's going to erupt. And on May 18th, 1980, it did. On May 18th, 1980, the pressure was so strong in this bulging area that it just blasted away the entire side of the volcano. The actual side of the mountain gave way in a giant landslide, which you can see here, it's sliding out of the way. And now because the side of the mountain that was holding everything in is gone, everything was able to blast out the side. And so these things are taking fractions of a second apart. And it just got bigger and bigger and bigger and bigger as the entire side of the mountain gave way. And this is all a pyroclastic flow, the height of the entire mountain. And you remember those things go 450 miles an hour? Yeah. So the force of that blast was so strong. This was a forest. These were trees, and they were completely stripped of all of their branches and knocked sideways by the force of this blast. It traveled a couple dozen miles and killed some 58 people in a matter of minutes, just because of the force of this blast. And when it was over, well, at first, then things started going up. But when it was over, what was left was that. So this mountain lost 3,000 feet of material in one eruption, in one moment. And this is now a little lava dome in the middle. So in the most violent eruption in United States history, certainly, and one of the most violent in the world. And this is what it looked like in 2012. So the landscape that used to be forested is now kind of barren and is still, like you can still see some of these trees and there's some flowers that are just trying to grow back. This was a massive thing. That is what stratovolcanoes can do. But they don't always do that. Sometimes they're just smaller eruptions, like in that video I showed you of Sakurajima. But yeah, these things generally, again, when you hear about a massive ash flow, when you hear about a volcanic hazard, when you hear about people evacuating from a volcano, it's from a stratovolcano. These are very, very common and very dangerous. Any questions about those? So Mount Shasta is one. We have a couple of these in Northern California. But any questions about stratovolcanoes before I go very quickly to the last one? Okay, time for the biggest boom. Okay, so calderas are the nastiest thing you can get. Calderas are the biggest boom. So this is where, this is the kind of thing where it, rather than looking like a mountain, looks like an indentation. Caldera literally means cauldron. And this is where you have a very, very high viscosity setting and an absolutely enormous volume. And the volatile content actually varies. Like you can, generally there have to be a lot, at least to begin with, but as we'll talk about in a second, it's not so much the volatile content that leads to the problem here, but also because this magma is so viscous, it can hold a ton of gas, even if like whatever gas is there is going to get trapped. And so this will occasionally happen in an ocean undercontinent subduction zone, but most often this is what happens when you have, again, one of those superheated hotspots, one of those plumes from the mantle burning through a continent. So it's the same kind of idea as Hawaii, except it's the complete opposite end of the explosive scale, because in Hawaii it just oozes because it's just basalt, but here it explodes because it's rhyolite. So does that make sense why this would be super explosive? When you have a huge amount of very, very sticky molten rock being fueled by an astonishing amount of heat from deep in the earth? Makes sense? Yep, so Yellowstone supervolcano is one of these. And it's hot because there's magma under there. But yeah, so the anatomy of a caldera might have a little bit of a mountain, but mostly we're talking about the center of it. Mostly there's this lower, flatter area in the middle. There might actually be even cinder cones or lava domes inside the caldera. And very often there will be a ring of sometimes cinder cones, sometimes stratovolcanoes around the edge of the caldera. And that's actually part of why these are so nasty. It's because they're kind of volcanoes within volcanoes within volcanoes. Yo, dog, I heard you like volcanoes. But anyway, so a modern example, so Crater Lake in Oregon is kind of a caldera. And so in this case, it's a smaller one. And it's an example that used to be a stratovolcano. It used to be, this is a continental and oceanic subduction zone setting. And in this case, this used to be a stratovolcano called Mount Mazama. But it blew its top. It just took its entire top right off and left Crater Lake, which is the deepest freshwater lake. And this little guy is a cinder cone inside the middle. So it's just, it blew up, it's gone. It's like Mount St. Helens, but worse. But even Crater Lake is only a small caldera. Really kind of the more typical caldera eruption. We've never seen one in human history because it would kill everyone. I mean, we've never seen one in modern human history. These are really bad. And they're also very rare because they take so much stuff to build up before they happen. But the way these things work is, so you have a massive, massive magma chamber under the caldera. But all of that magma is actually holding up the caldera floor. And so the way these things start to erupt is actually those volcanoes on the edges, the stratovolcanoes or cinder cones or lava domes on the edges of the caldera will start to erupt, and sometimes very energetically. But the thing is, once those start to erupt, and those might release pyroclastic flows and lava flows and gas and all kinds of things. But once those start to erupt, this magma chamber starts to get drained because it's not necessarily filling in as fast as it's erupting out. So as some of this magma erupts out as lava from the volcanoes, you end up with an empty space under the floor of the caldera. And air can't hold up rock, so the floor of the caldera collapses. And that's what's really, really bad. Because at first you had all of these smaller eruptions, but then when this collapses, first of all, you have the force of the thing falling, like we're talking something miles and miles across, falling down into a pit of lava. And so that releases an enormous amount of pressure. At least it releases a ton of gas. It releases a bunch of ash. You get massive pyroclastic flows. Often the floor of this will get shattered. Often there's enough shatters that then there's a difference in pressure, and then the magma will start erupting out the cracks again. Basically, this produces gigantic pyroclastic flows that can cover, that can be hundreds of feet thick and cause volcanic winter and just knock everything out, just because everything comes out the edges and then this collapses. And just the force of that collapse is enough to be a really big eruption. So does that make sense? How that works? Basically, as above, so below. What's got to go up has got to go down. And in this case, it goes down in a catastrophic explosion. We haven't seen it happen in human history, but we know it's happened. There's rocks from Yellowstone that cover many states. And there's actually a couple of examples of Yellowstone eruptions that cover large portions of the United States. And there's another example actually here in California. But before I go on though, it is now 3:15. Would you like me to go through the remaining 3 slides now? Or would you like me to start with finishing calderas before our test on Wednesday? Okay, I'm gonna quickly finish with calderas. If you gotta go, you gotta go. Go ahead, but I'm gonna finish this. Okay, so yeah, again, Yellowstone in Wyoming, you have a material that covers most of the United States. But there's another one that's actually less famous than Yellowstone, but is still really nasty. Oh, by the way, as a point of comparison, Mount St. Helens' ash only went this far. And Mount St. Helens is a small stratovolcano, but the Long Valley caldera in Eastern California is another super volcano. And the ash from that also covered everything in this kind of brown dotted line. So also like a third of the country. And this is what it looks like now. Like if you saw this, would you go, oh yeah, that's a volcano? No, right? It's a valley. It's called the Long Valley because it's a long valley. Have any of you been to Mammoth? Or heard of Mammoth Mountain? Anyone ski? So Mammoth is one of the subsidiary volcanoes on the edge of the Long Valley caldera. There are a lot of smaller volcanoes that ring the edge of this that have erupted until this floor has collapsed down and will eventually do that again. Yeah, and so the last time this did this was about 760,000 years ago. And the resulting pyroclastic deposits, again, cover many, many states, but they're especially thick here. Actually, before I go on though, you see how the valley floor is lower than what's around it? In this case, it's not because the mountains around it have gone up, it's because the valley floor went down. But now a lot of people live in here. I don't know how many of them know it's a volcano, but it is. This is not far from here. It's like a 4-hour drive. Yeah, maybe 5 hours. But this is the resulting ash bed. So this is called the Bishop Tuff. I think I might have mentioned this earlier, but this is all, you see how it's pink? It's rhyolitic material. It is all stuff that got launched out in these massive, massive explosions and was so hot that it just welded together into this extremely thick layer of rock. And here, again, there's not much sense of scale here, but this is several hundred feet thick in several places. And it's the thickest in Eastern California. It's the thickest near the city of Bishop, which is why it's called the Bishop Tuff. Tuff is Tuff, which is this kind of rock. It's what's called when you get a pyroclastic flow that kind of welds itself together like this. But this stuff exists in some form, again, over several states. But now if you remember this rock that I showed you on literally the first day of class? This is actually a piece of the Bishop Tuff. So now you can kind of recognize, oh yeah, this kind of is this texture. You can see chunks of a lot of little things that are kind of stuck together because this all erupted. This is all a bunch of stuff that got erupted out and then welded together and cooled. And this is actually from very close to Bishop. So yeah, that's calderas. They're the least common, the least, this is probably not going to happen in our lifetimes, let's hope, because there's mass extinctions associated with these things. We've gone full circle, yeah. I told you a lot of stuff would come back in this class, but these are catastrophic. There's a caldera called Toba in Indonesia that's actually associated with a major bottleneck in human evolution. Actually, geneticists have figured out that there is a sort of a massive reduction in human genetic diversity that is associated with the time frame of the Toba caldera eruption. So volcanoes are, calderas are a big deal. They're really scary, but luckily they're uncommon. But from a day-to-day standpoint, stratovolcanoes are the most hazardous because a lot of people live on stratovolcano islands. There's just a lot of them. But yeah, real quick, volcanoes give warning signs. They cause earthquakes, gas comes out of them. They visibly deform Mount St. Helens. You can measure heat. You can use things to measure magma movement. So scientists are just tracking this stuff all the time. And so there's volcano observation centers that look for these things, and they'll issue a warning if it seems pertinent. But really, volcanoes are nice in that they give warning signs. Once we get to earthquakes later, no warning signs for earthquakes. Earthquakes just going to do what they do. But volcanoes, you can monitor and warn people. So at least with all of these places like Japan, Indonesia, the Philippines, the Andes, lots of places where people live directly next to stratovolcanoes, or Hawaii, there's usually enough warning, and so people can get out of the way if they have the means to get out of the way. But yeah, I'm sorry for that. I'm sorry that was 5 minutes longer than I thought. I got a little excited with the videos. So that's it. That's the end of the material that's going to be on the test. That's it for today. I guess you could have left 5 minutes ago. But if you have any other questions, I'm going to hang out for a little longer and you can ask them. But if not, I'll put the quick quiz up. I'll put the link up for asking questions for the next test. And no class Monday. I will see you Wednesday. And thanks for hanging out. Promise I'll have some other lectures that are shorter to make up for this. So see a bunch of you are still in here. You have questions or? Oh, you went to Costa Rica last summer. Oh, cool. Yeah, right across from a volcano. Yeah, so Costa Rica has some really spectacular volcanoes, and a lot of them that are regularly active. And so those are also stratovolcanoes, because yeah, I would love to go to Costa Rica. I'm so glad that you had that experience. Everyone I know who's been there says it's awesome. And a great place to see a volcano erupt from a pretty safe vantage point. Yeah, that's awesome. I'm glad you got to go there before travel got ruined by 2020. Hopefully, yeah, thank you. Hopefully this gave you some more insight into what you saw there. See ya. Damani, okay, cool. I'm gonna end the class.